Clustering is about uncovering natural groupings in data. It has many applications, from grouping customers by purchasing behavior to clustering houses with similar characteristics. But what constitutes a natural grouping is ambiguous. There could be many correct options depending on perspective. Consider this dataset, for example. We could argue there are 2 clusters, or 4, or even 10. How many clusters there truly are isn't clear. But once we know how many clusters we want, it becomes much clearer how to organize the data into that many groups. For example, if we want to create 4 clusters, this is really the only reasonable way to organize this data into 4 groups. KMeans is a simple clustering algorithm that handles ambiguity by requiring upfront the number of desired clusters, then proceeds to do its best to organize the data into that many clusters. But beneath that simplicity lies a subtle mathematical assumption, a strong sensitivity to scale, and the reality that on some datasets, it simply doesn't work. This is how I think about K-means clustering. Stay tuned at the end of the video for the most challenging K-means problem that few are able to solve. Consider this two-dimensional dataset. Let's say we want to find 2 clusters. Intuitively, we would like the following points to all be part of the same group. Let's color them in blue, and all these points to be part of another group. Let's color them in yellow. But this is also a way to organize this data into 2 clusters. Hopefully you'll agree that this is an undesired outcome and just a bad clustering. But let's actually dig into why that is by comparing it to the previous clustering. Let's look at the blue cluster only. What do we like about the blue cluster on the left compared to the blue cluster on the right? The points are more tightly packed together, right? We can measure how tightly packed a cluster is by looking at how spread out the points are from the center of the cluster. And while that might sound straightforward, this is where things start to get tricky, because there are many ways to define spread and many ways to define the center of a cluster. K-means makes a very specific choice, and that choice is what makes the algorithm work. K-means defines the spread of a cluster as the sum of the squared Euclidean distances to the center of the cluster, and defines the center as the mean or average of the cluster. Let's add the mean of the blue cluster on the left and on the right. Now let's compute the spread of the blue cluster on the left. For every point in the cluster, we get its distance to the center, square it, and add it to the total. We can do the same for the blue cluster on the right. As expected, the spread is much greater on the right than it is on the left. We can do the same for the yellow cluster. And we can add those 2 spreads to get an overall evaluation of each clustering. This sum of spreads is commonly known as a cost function, as it answers how much does this clustering cost. As expected, the clustering on the left has a much smaller cost than the clustering on the right. Now that we have a way to quantify what we want from a clustering, which is that it should produce a clustering with a small cost, how do we find the clustering with the smallest cost? This is the optimization problem K-means aims to solve. Let's look at our dataset again, but with a different clustering. Let's add the cost on the side so we can track how changes to the clustering affect the cost. Take a look at the following point. If we zoom in, we see its distance from the yellow center is 2. In comparison, look at how far it is from the blue center with a distance of 4. Because spread squares distances, this point is contributing to the spread of blue quadratically more than points closer to the center. Since it's much closer to the yellow center, what would happen if we were to reassign it to the yellow cluster? The spread of the yellow cluster would go up, but since the point is much closer to the yellow center than to the blue one, removing it from the blue cluster reduces the spread of blue by an even greater amount. So the overall cost decreases. What we just discovered is that in order to decrease the cost of a clustering, we need to make sure that points are assigned to the cluster whose center is closest. Now that the point has been reassigned, however, the center of the cluster is no longer the mean. But adjusting the center by computing the true mean would change the spread. So although we decrease the cost by moving the points, could that be undone once we adjust the center to be the true mean? This is where we unravel just how intentional the definition of spread and center is in K-means. Consider that the cost is a mathematical function. It depends on things like the data, the cluster assignments, and the center of the clusters. But not all of these are actually parameters of the function. For example, we're not going to change the data in order to decrease the cost. The data is fixed, so it's not a parameter. Additionally, we just saw that in order to make the cost as small as possible, we need points to be assigned to the cluster with the closest center. Let's assume that that's already done, so assignments are fixed, and we just have a function that depends only on the centers. The question is, what value should the center take in order to minimize the cost? Recall from calculus, we can take the derivative and set it equal to 0 in order to find the critical points of the function. Because the cost is a sum of spreads, we can simplify things by looking at only a single cluster. Taking the derivative, setting it equal to 0, and solving for the center, we find the formula for the mean. Because the second derivative is positive, we learn this critical point is a minimum, not a maximum. So the center that decreases the cost the most is the mean. The choice of spread and center are mathematically very intentional. If we used a different definition of spread, a different center would be optimal for reducing the cost. For example, if we use the sum of absolute distances, the center would be the median of the cluster instead of the mean. Let's go back to our example. Adjusting the centers by recomputing the mean reduces the cost. After adjusting the centers, new points become closer or farther from the centers of these clusters, and we can reassign them, and adjust the centers again, and so on. At every step, whether we're assigning points to the cluster whose center is closest or adjusting the means, the cost decreases, eventually converging to a cluster assignments where the centers don't change and thus the assignments don't change. And this process will always converge. I know what you're thinking. Well, what if there's a point that is equidistant to two or more centers? Then which cluster it gets assigned to is random and we could end up never converging, right? Great question. Well, it's only random if you implement it that way, and there's no reason to implement it that way. Instead, use a deterministic choice, like always picking the first center in the list of possible centers. Okay, well, what if we get stuck in a loop, like clustering A, then clustering B, then clustering C, then back to clustering A? Well, recall the cost decreases at each step, and a clustering cannot have a cost smaller than itself, so that's not possible. But maybe the costs are all equal, like the cost of clustering A is the same as B is the same as C. That can only happen when points are equidistant to two or more centers, which we just established we would handle deterministically. What about convergence in the limit? What if the minimum cost is only found in the limit? That's also not possible because we have a finite dataset, and thus a finite set of possible partitions of the data. There cannot be infinite steps. So the process always converges. But will it always converge to the clustering with the optimal cost? And is the optimal cost even the clustering we want? Consider this clustering. It's clearly not optimal because this other clustering has a smaller cost and is more in line with what we expect K-means to find. And yet, this clustering cannot be updated any further. All points are assigned to their closest center, and all centers are the means of the clusters. It has converged. K-means is a deterministic process. So starting from the same set of clusters always produces the same result. So where we end up is completely determined by where we started. So how did we end up here? And can we avoid it? Let's take a step back and think about which clustering we should choose in order to kickstart this process of computing means and assigning points until convergence. One option is to start with a random clustering where you assign points to one of k clusters randomly. And while that technically works, it's not really in the spirit of k-means because it produces clusters where points aren't actually packed together. What's more, since each starting cluster will look like a mini version of the full dataset, all starting centers would be roughly in the same place. meaning at the next step, when we reassign points to the closest center, we would end up with similar sets of clusters every single time. To produce a much richer set of starting clusters that are more in line with the spirit of K-means, we designate points in our dataset as the starting centers. And now we have the full K-means recipe. We start with a random set of K-centers, assign points to the closest center, and update the centers to be the mean of each cluster. And we can repeat steps 2 and 3 until convergence. The starting centers then completely determine where we end up. Some starting centers produce optimal solutions, and some don't. Let's take another look at this non-optimal k-means clustering and rewind the clock to see if we can figure out just how we ended up here. We started with the following centers. Notice anything? Two of them are very close to each other, causing one cluster to be split into two. I know what you're thinking. What if we pick the first center randomly and every following center should be as far as possible from the previously picked one? That's a great idea, and it's called farthest first traversal. But for real-world datasets, it's not a viable option because it will always pick outliers as centers. And in this case, random would have been better. Could there be a way to combine the two? KMeans++ is an enhancement to KMeans that only changes the cluster initialization. Its initialization is as follows. Pick the first center at random. Then the second center should be picked with a probability proportional to the distance to that center squared. So points far from the center will have a much higher chance of being picked than points closer to the center. Picking the third center is a bit trickier because we have two centers. So we'll pick the next center with probability proportional to the distance to the closest of the two centers squared. That means that if the point is far from one center but close to another, its probability of being picked would still be small. To have a high probability of being picked, it needs to be far from both centers. This improved initialization is what makes KMeans++ a much better option than KMeans. But while we're more likely to find optimal clusterings with KMeans++, sometimes optimal isn't what we want. Cost doesn't tell the whole story since the following is an output of K-means. The cost is technically optimal, but it isn't the desired clustering outcome. Notice that if we manually assign each half-moon to a distinct cluster, K-means would notice that the following points are closer to the yellow center than to the blue center and would reassign them, thus converging to what we just saw. Neither is this clustering, where one cluster is highly elongated. Again, if we manually assign points to the desired cluster, the following points are closer to the yellow center than to the blue center and would be reassigned. Here's one more example. As you can see, K-means struggles with clusters that are not globular, well-separated, and similar sizes. But at the end of the day, clustering is ambiguous, and it's not always clear what the best clustering is and how many clusters there actually should be. Which begs the question, how do we know what value of k to pick? One big limitation of k-means is that we need to declare upfront how many clusters we want, but how are we supposed to know? I know what you're thinking. What if we run k-means multiple times for different values of k and compare the cost? The issue is the cost always decreases as k increases. In fact, the cost is 0 when k is equal to the number of data points. In this case, every data point would be in its own individual cluster. But that's not particularly useful, even though the cost is indeed very small. Looking at the plot of the cost as a function of the number of clusters, maybe we can find a point of diminishing returns. And this is a reasonable justification for the choice of k, but practically this requires running k-means many times, which is very costly, no pun intended. Sometimes the domain itself can help you find k. For example, for blood sample data, we know there are only 4 blood types, so depending on the application, we might argue k equals 4 makes the most sense here. When it comes down to it though, cost is simply not a good metric for comparing clusterings with different numbers of clusters. Cost is a measure of how tightly packed each individual cluster is. But we also want to make sure that we aren't splitting up clusters in the process. Metrics like silhouette scores measure at a high level tightness relative to how far clusters are from one another. And while that helps us hone in on a value of k, it still doesn't fully help us disambiguate between certain clusterings. Finally, the biggest pitfall of k-means is its dependence on a notion of distance. Features with higher scales or higher variance can dominate that distance, pulling clusters in their direction and effectively drowning out other smaller features. Feature scaling helps us balance the geometry of the space so that each feature contributes more equally. That said, scaling isn't always appropriate as it can remove important signal, like when features share the same units, for example. Differences in scale actually carry meaning. Let's quickly recap and jump into the challenge problem. K-means aims to find clusterings where clusters are tightly packed around their mean. Mathematically, it does so by minimizing the sum of the squared distances from each point to the mean of its assigned cluster, which is achieved in a two-pronged strategy, where points are first assigned to the cluster whose center is closest, then the center is updated to be the mean or average of the cluster. Each of these steps reduces the cost, and they're repeated until convergence. K-means kickstarts its procedure with a random set of initial k-centers. But if they're too close, they could cause a natural cluster to be split, creating a non-optimal clustering. K-means++ suggests a different initialization where centers are picked randomly, but with probability proportional to the closest of the centers picked so far. Despite this improvement, certain datasets are simply not suited for K-means. Now for the challenge problem. Given the following one-dimensional dataset, 1, 2, 3, 5, 6, 7, x, assume we run k-means with k equals 2, and we know that x is greater than 7. The question is, past which value of x will x always end up clustered alone no matter how we initialize k-means? I recommend pausing the video to try this out yourself. Here's my solution. There are quite a few ways we can initialize things. Let's first assume x is chosen as a center and some other data point is picked as the other center. In order for x to stay alone, we need to make sure that 7 never moves over to x's lonely cluster. In order for that to happen, 1, 2, 3, 5, 6, 7 all need to be together in a cluster, which has a mean of 4, and 7 must be closer to 4 than it is to x. So for this situation, x needs to be greater than 10. But we want a value of x such that x will be alone no matter the initialization. Let's say we start with 3 and 6 as our centers. Now we have the following clusters. Notice that if we start with 1 and 3 or 5 and 7, even though we generate different clusters, we quickly come back to 1, 2, 3 being one cluster and 5, 6, 7, x being another without x really impacting things. From this set of clusters, then, how will x end up alone? First, 5 needs to move over to the cluster 1, 2, 3. In order for that to happen, 5 needs to be closer to the mean of 1, 2, 3, which is 2, than to the mean of 5, 6, 7, x. So we just solve for x. So the mean of the cluster needs to be greater than 8, which means x needs to be greater than 14. We can update the assignments and recompute the centers. But now, since the difference between 6 and its center is 3, but 6 and the center of the first cluster is 3.25, it wouldn't actually move over. So we need to solve for x again, but from this specific clustering. So x needs to be greater than 14.75. Now that 6 has moved over, we can adjust the means, and now 7 is closer to 3.4 than it is to 10.875, so 7 moves over and x is alone in its own cluster. Thanks for watching. Like, subscribe, and help me spread this knowledge around if you found it helpful.